All right, let's get right into it. Today, we're going to unlock one of the most powerful problem-solving strategies for any coder, and that is the two-pointer technique. Seriously, it's a total game changer, and in this explainer, you're going to see exactly why.
You've been there, right? I know I have. You're staring at a problem with an array, and the only thing that pops into your head is nested loops, checking every single possible combination. I mean, it gets the job done, but you have that feeling in your gut that there's just got to be a smarter, way faster way to solve it.
Well, this is that smarter way. Just look at this. On the left, you've got your standard brute force method, chugging along at O of n squared. And on the right, the two-pointer technique, just cruising by at a slick O of n. And listen, this isn't some tiny little improvement. This is the difference between a solution that totally times out and one that just, passes with flying colors.
So, what is this magic? What is this elegant strategy that can just so dramatically speed up our code? Let's break it down. The concept itself is beautifully simple. Instead of having one pointer do all the heavy lifting, looping over and over again, we just use two of them. We typically start them at opposite ends of the array, and they walk towards each other, basically narrowing down the world of possibilities with every single step. Think of it like this. You're in a huge library, looking for two specific books on one very, very long shelf. Instead of you starting at one end and checking every single pair of books yourself, what if you and a friend started at opposite ends of the aisle and just walked towards the middle? It's that exact same logic. Start at the beginning, start at the end, and then move inward based on what you find.
Okay, so we get the what. But the really crucial question for any of us is, when do I actually pull this tool out of my toolbox? Let's build that playbook right now.
So here are the dead giveaways, the signals you need to be looking for. If you see a problem with a sorted array or a sorted string, that is your biggest clue. Red alert. If the whole point is to find a pair of things or a little subarray that meets some kind of condition, like adding up to a target number, your two-pointer alarm should be going off like crazy in your head.
And this isn't for some weird, obscure problem you'll never see. No way. This is the secret key to elegantly solving some of the absolute classic coding interview questions. Things like two-sum, checking if a word is a palindrome, or even removing duplicates from a sorted array, they all become almost trivial with this approach.
All right, enough theory. Talk is cheap, right? The absolute best way to really get this is to see it in action. So let's walk through a classic problem step by step, and you can watch the magic happen for yourself.
We're going to tackle two-sum 2. The setup is absolutely perfect for what we've been talking about. We're given a sorted array of numbers and a target value. Our job? Find the indices of the two numbers that add up to that exact target.
So here are our inputs for this example. The array is 2, 7, 11, 15, and the target sum we're looking for is 9. Let's do this.
First things first, we set up our pointers. We're going to place a left pointer at the very start at index 0, which is sitting on the value 2. Then we put our right pointer at the very end, that's index 3, which is on the value 15.
Okay, now we do our first check. We just add the values our two pointers are looking at. So 2 plus 15. That gives us a sum of 17.
Next up, we compare that sum to our target. We got 17, but we're looking for 9. So yeah, our current sum is way too large, not even close. So what's the move? This is the crucial part. Because the array is sorted, we know that to make our sum smaller, we have to get rid of the biggest number we're currently looking at. That means we have to move our right pointer one step inward to the left.
And that brings us to our new setup. The left pointer, it stays right where it is, at index 0. But the right pointer has now moved into index 1, and it's pointing at the value 7.
All right, time for round 2. Let's do the check with our new positions. We add the values up again. 2 plus 7, and that equals 9.
And there it is. Look at that. We compare our new sum, 9, to our target, 9. It's a perfect match. Bingo! We found it.
Now the problem asks for 1-based indexing, which is a common little curveball. So we just add 1 to our array indices. The left pointer was at index 0, so that's position 1. The right pointer was at index 1, so that's position 2. And that's our answer. Super clean, super efficient, and not a single nested loop in sight.
Okay, so let's zoom out for a second. What's the big takeaway here? Because this isn't just some neat little trick. This is a fundamental shift in how you can think about a whole class of problems. This is your new superpower.
So why does this matter so much?
Well, because it rockets you from a slow, clunky O of n squared solution to a lightning-fast O of n. It gives you this incredibly clean and elegant way to deal with sorted data. And, let's be real, it is an absolutely non-negotiable must-know technique if you're doing technical interviews.
This right here, this is the prize. ON, linear time. It just means we only have to make one single pass through the array to find our answer. That is the power we've just unlocked.
And look, if you take only one thing away from all of this, let it be this right here. Burn this question into your problem-solving brain. The next time you're reading a problem and you see the words sorted array, this needs to be the very first question that pops into your head. This technique, it's like a key. So the question I'm going to leave you with is this. Now that you have this key, what other classic problems, what other locked doors could this elegant approach open up for you?